Today we will illustrate chapter 11, work and energy. When can we say that a force has a work? A force has a work if it causes the displacement of an object upon which it acts. What's the value of this work? Work equal F vector dot D vector equal F dot D cosine alpha. Alpha is the angle between the force and the displacement. The unit of work is joule. Work is a scalar quantity. It is not a vector quantity. Note that if alpha equal to 90, then cosine alpha equal cosine 90 equal to 0, and W equal 0 joule. So any force F which is perpendicular to the displacement, since alpha equal 90, has no work. Work is of two types, motive work and resistive work. Motive when alpha between 0 and 90, and resistive when alpha between 90 and 180 degree. Let us start with motive work. If alpha between 0 and 90 degree, then cosine alpha positive, and the sign of W will be positive. In this case, we say that work is motive, that is the force F which has a work facilitates the motion of the object. For example, if alpha equal to 0, then work equal F dot D cosine 0, cosine 0 equal 1, equal F dot D. When say alpha equal to 0, this means that the force and the displacement are parallel to each other and have same sense. Same thing for all values of alpha between 0 and 90. What about resistive work? Resistive work means alpha between 90 and 180. In this case, cosine alpha is negative and W is smaller than 0. For example, consider the force of friction. We note that the force of friction always opposes motion. So Fr is always opposite to the displacement. So the angle between Fr and the displacement is 180. And cosine 180 equals -1. So in this case, work equal F dot D cosine alpha, cosine 180, equal minus Fr dot D, because cosine 180 or cosine pi is -1. So we can write directly work of friction equal minus Fr dot D, because the friction opposes motion. Okay, now what is the work done by weight? Work done by weight may be positive, may be negative, and may be 0. If the weight is perpendicular to the displacement, then the work done by weight is 0. But what if the weight is not perpendicular to the displacement, like an object moving on an inclined plane? For example, work done by mg equals mg h initial minus h final. Hi is the initial height from the reference, and h final is the final height from the reference. This is the general equation we have to apply. For an object moving down an inclined plane, for example, this is an inclined plane. The inclined plane makes an angle alpha with the horizontal. This is the object. Now draw two axes, x-axis and y-axis. This is the x-axis, y-axis, and this is weight, mg. Weight mg has two components, on x component and y component. The projection of mg on the x-axis is mg sine alpha, and the projection of mg on the y-axis is mg cosine alpha. So work done by mg equal work done by mg cosine alpha plus work done by mg sine alpha. Work done by mg cosine alpha is 0. Why? Because mg cosine alpha is perpendicular to the displacement. In this case, look, mg cosine alpha perpendicular to the displacement. This is the displacement, which is the inclined plane. This is mg cosine alpha. The angle between them is 90. What is the value of work done by mg sine alpha? Equal mg sine alpha, take the eraser, equal mg sine alpha times the distance covered on the inclined plane times cosine 0. Because in downward motion, the angle between mg sine alpha and the displacement is 0, parallel to each other and of same sense. For work done by mg equal mg sine alpha dot d greater than 0 motive work. So always for an object moving down an inclined plane, I say down an inclined plane, the work is always motive equal mg sine alpha dot distance d. What if the object is moving up the inclined plane? For example, now clear the page. For an object moving up the inclined plane, this is inclined plane. An object is moving from point A to point B. A is at a height HA. B is at a height HB. This is the object. And this is weight, mg. Similarly, like in the previous, work done by mg for an object moving up the inclined plane is mg dot displacement AB, but in this case, the work will be negative. Let's see. Work done by mg equal work done by mg, or we can use the other formula also, equal mg HA minus HB. Okay. equal mg HA minus HB equal. Of course, HA is smaller than HB, so HA minus HB will be negative, and in this case, the work will be negative, and so it is a resistive work. But what if HA and HB are not given? Their values are not given, but we have the value of AB. How can I calculate HA and HB? In this case, we take a horizontal from A, this angle of inclination alpha, and also this angle is alpha. We say that sine alpha equal opposite. This is the opposite of alpha. This is the opposite of alpha. Sine alpha equal HB minus HA over AB implies that HB minus HA equal AB sine alpha. So sine alpha opposite, this is the opposite, HB minus HA over hypotenuse AB. So HB minus HA is AB sine alpha. Let us come now to the work done by mg. Equal minus mg AB sine alpha. Why is minus? HB minus HA is AB sine alpha. HB minus HA is AB sine alpha, but in the formula we have HA minus HB. So HA minus HB minus HB equals minus AB sine alpha. So substitute, instead of HA minus HB, we get work done by mg is minus mg AB sine alpha smaller than 0, resistive work. This is how can we calculate the work done by weight or work done by gravity. Now, let us continue. So as we said, work done by weight, mg h, h initial minus h final may be positive, motive, and h initial minus h final may be minus h negative, resistive. This is an example. Consider a box of the adjacent figure, knowing that it is displaced 15 meters as shown in the figure. Calculate the work done by weight, normal, and applied force, and then deduce the total work done on the box. Of course, work done by N will be 0. Why? Because N is perpendicular to the displacement. Work done by mg is also 0 because mg perpendicular to the displacement, where the displacement is, of course, to the right, as you see. And work done by capital F, F vector dot D vector, which is F dot D cosine 0, because the angle between the force and the displacement D is 0. So work done by capital F is motive, and work done by friction is Fr dot displacement, but Fr is opposite to the displacement. The angle between them is 180, and cosine 180 is -1. So we get work done by friction is Fr d cosine 180 minus 270 joule. It is resistive. What is the total work? The total work is the sum of all these works. Another example, as we illustrate before, for an object moving on an inclined plane, calculate the total work done on the box of the adjacent figure when it moves 5 meters down the inclined plane. Work done by N is 0 because N is perpendicular to the displacement. Work done by friction, as we said before, you can write it directly minus Fr dot displacement. We have Fr 4, displacement 5, so work is minus 4 times 5, which is minus 20 joule. Let us come now to the work done by weight. Work done by weight is mg times d cosine 60. Okay. Equal. إذا نيجي هلا للwork done by weight, we have a distance 5 meters. We can calculate it, of course, in this case. Second method. Work done by mg is work done by its components, mg sine alpha, and work done by mg cosine alpha, as we said before. What is the work done by mg cosine alpha? Work done by mg cosine alpha equal to 0 because mg cosine alpha perpendicular to the displacement. You can put it 0, and there is no need to write mg cosine 30 d cosine 90 because you know that mg cosine alpha is perpendicular to the displacement. What is the value of work done by mg sine alpha? As we said before, in downward motion, work done by mg sine alpha equals mg sine alpha times the distance d times cosine 0. Why cosine 0? Because as you see, mg sine alpha have same sense as d as the displacement and parallel to it. So it's mg sine alpha, this is the force, times d cosine 0, which is 1, and we get work done by mg equal 50 joule. Of course, this is all things about work done by a force. Thanks for your listening.